Okay. So we're going to look at two ways to interpret any model. Okay. In this case, the model is going to be the random forest model. I think one of it you guys already know. So it's not just for random forest though. So it can be useful for any forward stage wise additive model, for example. Okay. So things like AdaBoost, if you have done AdaBoost but you have used decision trumps or decision trees, you can just use the same idea. Okay. So that's a quiz question or an exam question, that whether variable importance idea can be used in other models. Okay. Um, So what do we want is interpretability, and there are various levels of interpretability. First of all, I guess the ideal gold standard is if you make a prediction, that this person's loan is denied or approved, you want to really understand what led to that process. Okay, what variables and why did they combine in certain way in a very interpretable way to figure out why something happened. Okay, and that's kind of critical, especially when your systems are interacting with humans and making decisions in this type of an automated fashion, like loan approvals, or somebody getting a bail or not, or somebody getting a financial product or a credit or not, things like that. Okay. um, so here's a simple way that some of you have seen. um, So what we're gonna do is try to write get a measure of variable importance. Okay, which means that for each variable I have capital little p number of variables. Right. So for each variable I just want a number, a score of how important that variable is to the prediction problem. Okay, at hand. So here's a score. So I'm gonna use this symbol IL square. Okay. Uh, as the score for the health prediction. Okay, sorry, health variable. Okay, so there are p number of variables. So health variable, I'll have a number. That number is just is the average of uh, so again, I mean, this looks like a messy formula, but all it's saying is, oh, we have a tree. Let's say we have a single tree for simplicity. We can extend. I'll extend this to multiple trees, which is random forest tree soon. So let's say we have a single tree. It will have capital J regions, or not regions, but capital J internal nodes. Okay, internal nodes means just the not the final regions, but the region which got split into this final region. Okay, I mean, and all regions before it. Okay, so everywhere where you decided a split is a node index, and that's index from t is equal to 1 to capital J. Okay, so those are some number of. So if I had a tree. Then these are the internal nodes. These are the three internal nodes. Okay. So for each node, you're just saying, oh, was this the node? Was the split choice variable? Was it the health variable? Okay. Very simple question. It could be health variable. It need not be health variable. If it's a health variable, then it's an indicator of that. Okay. Just means that I'm going to start counting. Okay. I'm going to include it. And what is this term? I had t. Okay, I had t is just the improvement or the delta in the, for example, the mean square error. Okay, so just saying before the split and after split, there was some mean square error, right? So at the region, there was some constant currently. I split it into two regions, and there are two new constants. That gave me some mean square error total, and before that I had some mean square error. The difference between those two is the uh, uh, I had t square. Okay, square is just think of this as notations. You can drop the squares if you want. This and remember, like every time you split, you actually decrease the mean square error anyway. So it's like before the split minus after the split, this number is positive. Okay. So it's basically saying, oh, was this variable used in some splits? And if the variable was used, well, did it cause a huge decrement in the mean square error? Okay. If it did, then there's a large term here, right? And if that variable appeared multiple times, then there's going to be several such terms. And if the variable was really important, then it appeared in many split points, and the improvement was, hopefully large at every split point. And so that's the total improvement due to that variable. Okay. That's what this is. Okay, and you can compute this for every variable. So there are going to be p numbers, and that's it. And then rank order them, and so you get a variable importance score for each variable. Okay, and I think some softwares again in the notebook. What they do is they order them. They order them, of course, according to the scores, but they also renormalize the scores. Okay, because the scores can be anything, any positive number. So just scale the last number, I mean the highest number, to be between 0 to 100, so that every other number is like multiplied with the same constant. So you can see that, oh, it's 100% important, or whatever is the interpretation you want to give here. Okay. So that's the importance of these variables on in this case California housing data set. These variables on the prediction, the output. Okay. Any questions about this? I think this is too fast. I think in some other class maybe you spend some time on this.
So, if we run this in our random forest and just find out the importance from
Yeah.
the tree, it gives us on the basis of maybe accuracy or mean degree training. So, what is the range
On the basis of accuracy and
mean decrease accuracy or mean decrease training?
yeah,
Those are-
yeah,
So, what are the ranges for both?
that's these.
Like ideally,
What are the ranges for
yeah.
the
So
decrease?
when they give the results, what can be the range of? Yeah.
First of all, I didn't extend this to random forest. I mean, so random forest is average over all trees. Okay, for the same variable. In this case, variable L. You have one score like this per tree, so you can just average over all the trees to get average, or actually sum over all trees, sum over all trees actually, to get the total score. Okay. Now, with regards to this, I had could be the decrease in the mean square error, or the decrease in the Gini index value, or the decrease in entropy, or whatever it is. Okay. There is no bounds for how much it is. Okay, actually these things you should be able to code up yourself. I don't know if you're gonna use package and read the documentation. They could have their own variations and interpretations, but this is a general idea. Okay. No. Okay, so let's look at the next idea, which is partial dependence plot. Okay, so partial dependence plots, again the objective is the same. Understand what is the model that I built. Okay, right. So the way you understand it is, let's say f of x is the model that you have, and we're going to split it into two parts, x s and xc. Okay, xs and xc, just think of it as splitting the coordinates, splitting the features. Maybe you care about dependence on a couple of features, like maybe education level and income, and maybe everything else, xc is the complement, so everything else is like the other features. Okay. Okay. So maybe I care about, I built already a function. Let's say this function f. It could be a random forest model, or it could be a boost model, or it could be a gradient boosted machine. And I just want to know the dependence on two variables. Okay, this function is a function of two variables. Let's say income and education level. And how do I do that? Okay, so I just named the variables as xs and xc. The idea is very simple. What we want is fs of xs. Okay, so this is called this is a partial function. I mean, actually, some of you might have seen partials in. Have you used partial in Python, for example? Some of you. Okay, so look it up. It's a nice function. But so what we want is fs of xs. Okay, this is a new function. Okay, it's a function of only xs. Okay, when for example it's only a two-dimensional function, and it's gonna be equal to expectation over all these other variables of f of xs xc. Okay, so very simple idea. All it's saying is, oh, if you want to find the dependence of your function, your full function, on a couple of variables, then you average out the effect of all the other variables. Okay? Note that this is not the same as f of xs and expectation with respect to xc of xc. Okay, these two are different. You can't plug in the average value of the other variables and then figure out what is the dependence on your uh, the features of interest. Okay, you should take the average of your prediction over all the other variables, average it out, and then you'll get the dependence of your your outcome. How does your input variables of interest like income and education level influence some outcome like something. What is the confusion here? Okay, not this part. You just want to understand this. Okay, so here we are saying that we care about understanding the dependence of a couple of variables of interest. Let's say, I mean, this it says plot. So maximum plot we can do is 3D plots. So let's say xs is two-dimensional. We want to find the dependence. So we already have built a function, okay, some random forest model. We just want to find the dependence on how do two of the features influence my output. Okay, and everything else is xc. Okay, other features, other feature coordinates. The way to do it is to average out the other features. Okay, so as if go to the training data. Okay, maybe pick the first two coordinates like income and age, sorry, income and education level or something. Okay, they'll subset the data, and there'll be some hopefully some observations which will correspond to different xc values. Average out your prediction over those xc values. Okay, so that's going to be your dependence of your output on just these variables. Okay. It's just averaging out the effect of. I mean, it's like marginalization, but the marginalization idea has been written in a slightly different way. Remember, if you had a joint distribution between multiple random variables, how to get rid of some random variables? You integrate out the variables which are not of interest, right? So that's what's happening here. Okay, I'm just saying that this is not equal to this. Okay, okay. There are some situations where this is equal to this. Does anybody know which situation this is the case? When can you push the expectation inside the function? What's it? Uniform. One candidate solution. What else? Okay. You can push the expectation inside a function if they are interchangeable, right? When are they interchangeable? When this function is linear. Okay. So when f is linear, you can see that, right? If it's beta 1 times xs plus beta 2 times xc, then of course you can push the expectation of or xc into the second term only. Okay. But not just uniform stuff. Okay, that's partial dependence plot. Plot is only because if once you have xs being two-dimensional, you can plot it and see the trends. Okay, see the output. How does it vary as you vary inputs? Okay. So now let's look at how much time do we have? So now let's look at another model. It's called MARS. Really cool name. So let's understand what is it about. It's going to be an example of a additive model. Okay, so it's going to be composed of many small models together added together. Okay, and why are we studying this model is just an example to serve only one goal, which is here's an example of a model construction process. So you can have your own descriptive model construction process in general in terms of like a stage-wise additive model or things like that. So here's an example of a model construction. And it also tries to capture, there's some intuition for this model that I also point out. Okay, just like random forest had some intuition, right? Decorrelate trees because you're subselecting m coordinates out of p coordinates in every split choice. Okay, so here the model is of the form f of x is beta naught plus sum over m is equal to 1 to capital M of beta m hm of x. Okay, so hm are these base functions which are getting added together with some weights in front, and that total is going to be your prediction model. Okay, sum of them is going to be a prediction model. So very similar to, I mean, you will see this form again and again quite a bit. You've seen it last in the last lecture. So, but the way we construct this particular, I mean, so multivariate additive regression spline. So first of all, it's for the model is for, I guess, regression, and additive just means there is an additive form like this. Okay, multivariate just means x and these functions are multivariate functions. Okay, splines is because you'll see that there are some specific functions that we're gonna kind of use, and these are certain types of spline functions. Okay, splines are certain types of functions. We're gonna look at specific spline functions. Okay. Um, and for that, here's what I'll start with. So we have data x, okay, and xij. Sorry, I think I put the dashes too much, but this is xij is the ith row jth entry. Okay? We know this. I mean, this is our data set. I mean, at least the feature side. And given that, we're gonna every entry xij is gonna give us two functions. Okay, the first function, let me call it g1 of x, is going to be x minus sorry x j minus x ij plus, and g2 of x is x ij minus xj plus. Okay, there are two functions. X is p-dimensional, right? Input is p-dimensional, output is a number. Okay, I'll tell you what this, I'll interpret it, tell you what this function is. It's a very simple function. It's just saying, I mean, so first of all, let's fix on one entry, one point here. Each number in the data matrix is corresponding to two functions, right? So what are these two functions? These two functions are actually, although their input is p-dimensional, they're actually functions which are only functions of the jth coordinate. Okay, in this case, they are the functions of only jth coordinate because I'm using xij, which is the numbers in the jth column. Okay, that's why it's only functions of the jth coordinate. And in fact, how do these functions look like? These are functions. Let's call xij as the black dot there. Then the first function g1 is a function which is like this. Okay, so 0 and some 45-degree angle here. That's a function. Okay, so this function, although this notation, all it means is that, oh, if my jth coordinate, jth coordinate, it's a variable. If it's less than xij, then it's 0. If it's greater than xij, then the difference is what this is. Okay, it's a 45-degree line. Okay, the plus just means that xij minus this. If it's positive, then output that number. If it's negative, then output 0. Okay, the opposite function is the same. It's just saying if xij is smaller than, sorry, xj, the variable, is smaller than xij, then output this minus this. Otherwise, output 0. So the other function is just symmetric. Okay, it's basically something like this. Okay, that's the second function. So this is g1 and g2. And what are these functions trying to capture? I mean, these are, you can also call them basis functions. They just try to capture, you know, some regions of the space. Okay, in the sense that if so, what are these functions supposed to do? These functions are going to eventually end up in these functions. Okay, hm's. Okay, now what is this objective of this guy? this guy is supposed to approximate my conditional expectation of y given x. Whatever is the final target, hopefully it approximates that really well, right? So these functions have this nice feature that they are zero for part of the input space and only non-zero in some other parts of the input space. So they can capture local trends, okay, in a nice manner. And I'm gonna repeat that pretty soon, how they'll capture it. So these are, let's call these the basic functions, okay, basic functions, and there are n times p of them, pairs like this, and we're gonna build our HM functions, which are part of our final solution in an iterative way using these basic functions. Okay, so that's the goal now. Any questions? Okay, so the constructive procedure is that we'll have so call these functions script C functions. Okay, in the sense there are np of them for every data point. There are a pair of them. So put them all together. There are many functions. Okay, let's call them script P. That set of functions to be script P. Okay, they are fixed functions, right? Like these functions, these hinge type of functions. Okay, these are called hinge functions as well. Those are splines. Okay. What we'll maintain is the following. Okay, so what we want, our goal is plus sum over m of beta m x. Okay, so this is what we want, and we have the script C, right? Those set of np functions. Now we'll start with the base case where our function h0 of x is the constant function. Okay, it's not predicting anything, it's just constant. Okay, if it's constant, then you can think of h0 as like a multiplier to beta naught. Okay, it's a constant function, so I need to make a prediction. What's the best prediction I can make if I'm not using any features? Is just whatever is the outputs mean. That's what I should make a prediction for, right? If I'm doing regression with square laws, right? So I'll put this function in a set script m. Okay, so what is script m? It's going to be a bunch of functions where I'm going to keep adding more and more functions. Starting point is just a constant function. Okay, now I need to figure out what is the next set of functions to add. Okay, so it's an iterative procedure. Ultimately I have to have capital M number of functions eventually, right? That's my total number of functions here. I start with a simple function, which is nothing. It's a constant function, and now I'm going to start adding some functions. Okay, and I'll stop when its total number of functions here is capital M. Okay, I'm going to add functions based on these functions, basic functions. Okay, I'll start with that. So these are the types of functions I'll add: beta 1 times 1 times x j minus xij plus beta hat 2 times 1 times xij minus xj plus. Okay, so these are like our g1 g2 functions. Okay, so my first choice is that I'm gonna, from here I have np such choices, right? The different xij's, there are np of them. I have different choices here. What I'm trying to say is that I had only one function here, so that's a constant function. That's going to be a multiplier, okay, here. And I'll try np different choices here. If I pick xij, there's only one function like this, one function like this, right? So this is a candidate new part that I want to add. So this plus the constant function doesn't give me the lowest mean square error, okay? So I have so many choices here. I'll use different choices, I'll get different betas, and there'll be some beta choice and xij choice which will be the lowest error. Okay, then those two functions will go in here. So maybe from h naught maybe I have h1 of x and h2 of x, which is I think in the notes it is x2 minus x7. Okay. These are the two functions I added. Okay. And there's going to be some corresponding betas. So now I have a bigger set of script 10. I added two additional functions here. Now I want to add in this case, 0, 1, and 2, 3, and 4. I want to add two more functions. Okay. The way I'm going to add it is look at, oh, can I still consider h0 a function from this side and these NP functions as multipliers on this side. Okay. So the first choice will be still 1 times 1, so 1 and 1, and the choice function from script C. The second choice will be this multiplier instead of 1 times this choice function from this script C. And the third choice would be this function as a multiplier and then choice function from script C. So you see, ultimately my terms, Hn terms, look like products of these base hinge functions. Okay. This Hm, for example, let's say my next choice was H1 is this instead of 1, this hinge function times another hinge function. Okay. So let's say that happened to be the best choice. Then the next functions that go in here are going to be that product of two hinge functions. Okay. Is that clear? So the next choice would be H0, H1, H2, and then H3 could be x2 minus x72 plus times x5 minus x25 plus, for example. And similarly, H4 could be times something else. Okay. So all I'm saying is this is how you would add functions, and these functions are splines. Okay, starts, these are spline functions, and this is the additive model that you're getting. Okay, so every round I'm adding functions, figuring out the best coefficients, and minimize the mean square error. So very simple, like a pretty naive idea. But what is that we're achieving by the end of the day is that because these functions are like hinge functions, okay, basically flat and then going up. So you can imagine if I have two such hinge functions, okay, if I have two such hinge functions, okay, one function is going flat and then raising up, right, like this, right, like up, and then let's say there's another hinge function which is going like this and rising up. Okay, now you can see that there's a flat function and going up this way. There's a flat function going up this way. Then the only place that's non-zero is over here. Okay, so three of the spots it's 0. Okay, so these functions are somehow capturing the local, can capture the local trends in the final target function that you care about, f of x, conditional expectation of y given x. Okay, because these functions are somehow sparse, they're non-zero in very small region if they're getting multiplied compared to being 0 elsewhere, basically. So very simple idea, and this model seems to capture that idea. Okay. Any questions? If not, let's move to support vector classifier. Okay. So what we'll do in the next 15 minutes is only focus on one point of view. Okay. So this is going to be eventually next class we're going to talk about nonlinearity. So remember, by the way, the Mars model that we saw is a nonlinear model. Random forest model is a nonlinear model. Tree-based model is a nonlinear model. Now, actually, for the next 15 minutes, we're going to look at a linear version first. Okay. Understand the geometric idea first, and then next class we'll kind of go back to the nonlinear world for this guy. Okay. So now we're going to look at linear model. Okay, linear variation of support vector classifier. And for that, the intuition for this is it's going to be a linear model. So you can say, oh, how many different variations of linear models can you have? A linear model is just linear model. It's just as a hyperplane. right? In fact, it's for classification, so it's just going to be a hyperplane, which is going to be a decision boundary, and that's it, right? Nothing much going on. But what's different is that we're going to motivate the choice of the loss function or the optimization, okay, to pick a linear model using some geometric ideas. Okay, that's all. So the difference is that we'll have a geometric intuition for choosing this hyperplane, which is the decision boundary which separates the two classes. Okay, so we are in fact going to be in a two class classification setting. And our classifier, even before even doing anything, is going to be characterized by x such that f of x is equal to 0. Okay, so this, it's a two class classifier, so there has to be decision boundary. So I'm writing the classifier in terms of the decision boundary itself. Okay, and that f of x itself is x transpose beta plus beta naught is equal to 0. Okay, so that's the hyperplane. This is the definition of a hyperplane. Okay, so in two dimensions, um, you can think of x1, alpha 1 x1 plus alpha 2 x2 plus some constant is 0. Okay, right? Like for example, so this is x1, this is x2, then this is x1 plus x2 is equal to 1, something like that. Okay, so 1 times x1 plus 1 times x2 minus 1 is equal to 0. That's this equation. Okay, it's a hyperplane or a plane in a line in two dimensions. Okay, so what we want, so starting point, we'll also make another assumption, okay, which is about separability, and we'll relax it towards the end. Separability just means that, oh, I have two classes. Let me think of, I should be able to slide in a hyperplane such that I can split these two classes into two separate regions. Okay, so basically, a hyperplane splits the input region into two regions, right? Hyperplane splits the input region, the full region, into two regions. Okay, so we're just saying that the data is separable. In this case, the data is separable, as the instance is separable. Just means that in each of the two regions there will be one class. Okay, only one class. In one of the regions there will be positive class, in the other region there's going to be negative class. Okay, so something like this in two dimension. Okay, something like this. This is separable because at least in the training data, all the circles are on the bottom and negatives are on the positive on the top. Now, how do we choose this hyperplane? How do we choose a model? Okay, a model is just choosing this hyperplane, right? And choosing a hyperplane is nothing but choosing beta and beta naught, right? So how do we choose this? The question is, there are many choices, right? I mean, data is separable, so I could slightly shift the line up. I'll still be able to separate the data set. Okay, so it's not clear which is the right choice. Okay, and instead of taking a loss centric view directly, so we're going to look at a geometric view to make this choice of, because we have so many choices from picking hyperplanes here, it could be slightly rotated and still have zero training error and so on. So we want to pick the best one. Okay? So that's what we want to do. And for that, we make the following observation. Okay, if you have a hyperplane, okay, and let's say there's a point x outside the hyperplane, and let's say there's a point on the hyperplane. Okay, so that's x over there at the top. This is a hyperplane. There are points on the hyperplane. So this is the closest point in the hyperplane to x. Okay, let's say this is the point. Okay? That point has to be basically is orthogonal. So not that point itself, but this point is basically a projection of x. Okay, it's a perpendicular projection of x onto this hyperplane. That's what I mean. And let's call this point P. Okay, so we can think most of these guys in terms of vectors. Okay, so a hyperplane. In the last slide, I wrote the definition for the hyperplane, that it was x transpose beta plus beta naught is equal to 0. Right? That was the definition of the hyperplane. Exactly, the points that lie on that plane are satisfying this equation. Now we know that the point P satisfies that equation, and x doesn't satisfy that equation. But there's a distance between x and that hyperplane, right? That distance, let's call it. I want to call it m. Okay, I can call it something else, but let me call it m. And so we know this point P transpose beta plus beta naught is equal to 0. Okay, point P is on that. The point P as in this vector is on the hyperplane, right? So this is the origin. So P is some vector like that. Now this the relation there's a relation between x and P. Okay, the relation between x and P is that you can see, right? So if P is a vector here, x is a vector there, P plus something is equal to x. Okay, that something, okay, that length of that something is m, because that's what I said. The distance of the point to that plane is m, and so x is equal to P plus m times beta vector divided by the norm of beta. Okay. So what is this? This is the perpendicular vector. Beta divided by norm of beta is the unit vector. Okay. It's a unit vector. That unit vector is always perpendicular to this plane. Okay. We're just saying, oh, if it's a unit vector, scale it up by m. That plus the previous point is the point x. Okay, because we said P is the projection of that point. So that's why this relation holds. Okay. And so we can substitute instead of P over here to get x minus m beta divided by norm of beta times beta plus beta naught is equal to 0. Right? Okay, so maybe I should put tags and transpose. So x transpose beta minus m times norm of beta plus beta naught is equal to 0. Right? I'm just multiplying this with this. M times beta transpose beta is just norm of beta square. Okay. They get cancelled. And this sum is just as before. Right? So this implies x transpose beta plus beta naught divided by norm of beta 2 is equal to m. Okay. I mean, I just brought m to the right hand side and put everything else on the left hand side. Now remember, m was the distance of the point x to the plane. Okay. So here is the closed form expression. Okay, we just derived something that we should be knowing from geometry, which is how far is the point m to a plane. It's just that point transpose beta, the parameter of the plane, plus offset divided by the norm of that normal vector to the plane. Okay, so this is a known. So now let's go back to the geometric intuition here. Okay, so for any point, minus point, circle point, any point, we know its distance to the plane. Okay, if we know its x location, right? If we know its location, we know the distance to the plane. So what we want to do is for every point to be at least some distance away from this hyperplane. Okay, I want to prefer those hyperplanes or prefer that hyperplane which is farthest away from any of these points. Okay, that's the geometric intuition. I want to find a plane which is the farthest from any of these points. Okay, and for every point, I know what the idea is. I mean, what the distance is. I mean, for every point. Okay, and another fact, because we chose binary classification, and did I use G or Okay, let's call it yi. Yi are the classes. Let's say they belong to -1 and 1. Okay, with some abuse of notation. Instead of using g, I'm using y's. I'm saying y's can only take either +1 value or -1 value. Okay, so that's the simplicity. Now we wanted a hyperplane which is farthest from everybody, all these points. So what we can do is to impose the following constraint, okay, which is that yi times x transpose beta plus beta naught divided by norm of beta is greater than or equal to m for I is equal to 1 to n. Okay. Why does this make sense? Why did I suddenly bring in a yi and multiply with this? Is because remember the distance should be positive. Okay, so in the previous slide, I did not put an absolute value here. Okay, so if points, so there's some. I mean, if I put an absolute value, then that's the distance of a point to a plane. Okay. Otherwise, points on this side and points on this side will have opposite signs. Okay, in terms of the directionality of the vector. Okay. So that I can capture in terms of this yi. For example, let me assume that the negatives are such that yi is +1 for them. I mean, in my diagram. So +1 times, let's say for that direction, these numbers are positive. So for the negatives, the distance is at least m. And for the circles, yi's are -1, but these are like the sign distance, which is also negative. Okay, so that their product is still at least m units away. Okay, so for all points, I want the distance to be at least m units away. Okay, so that's my preferred hyperplane. I want beta and beta naught such that this is true. Okay, and so that I can write as well. So max over beta, beta naught, and m also because I can maximize m of some quantity. Okay, I'm going to use 2m, but so m is the gap, right? M is the gap of this hyperplane to the closest point on either side, right? So 2m just means it's like the total band. Okay, so as the circles, negatives. So m is this. This is m. Okay, 2m is on m on both sides. Okay, so this is what I want. So this is the starting point for support vector classification's objective, optimization problem. So this is it. So I want to find beta and beta naught such that they have the maximum. I'm using the notation m for a reason. It's called the margin. Okay, it's called the geometric margin. Okay, so this is the geometric interpretation for the choice of the linear model that maximizes the margin, okay, over my separable data set. Okay, since my data set is separable, I can write it this way. Okay, these are distances of points and sign distances, so I can multiply with yi's, and they are ensuring that the distance is at least that much. Okay. Any questions about this part? Okay, so since we are running out of time, there is actually we're gonna again revisit this formulation next time. But what will change is that I'm gonna drop this notion of separability. Okay. So here, separability just meant that circles are on this side, negatives are on the other side. Okay. For this is optimization problem, in which actually I can drop m as well because of some one additional degree of freedom. I can either, if I scale up betas and I can scale up m, it's all the same equation. So I can drop m. But I will revisit this point. But next time, what's going to happen is that I'm going to draw the separability assumption and also write what is called a dual optimization problem. Okay, and that's gonna give us the notion of what are support vectors. Okay, so writing the dual program is the biggest challenge, and it will require some assumptions, and for at least for us. Okay, um, and that's it. So those are the two big things, and then we'll make it nonlinear. Okay, so let's stop here, and we'll resume next time.